Welcome back, everybody. This is our fourth video on using integrals to find volumes of solids. In this video, we're going to switch things up a little bit by changing the axis of rotation. Well, we've done that a lot, but we're going to change it not from something parallel to the x-axis, but make it parallel to the y-axis. That's going to be the big difference here. So instead of, say, for instance, taking this region and rotating it this direction, we're going to rotate it around this direction, right? Around the y-axis, or maybe something which is parallel to the y-axis. So let's try to visualize what's going to happen there. So first, when I rotate this around, okay, we'll get another copy of it on the other side. So it's going to look something like that. And then, of course, it's rotating, so we get these nice circles. And, well, the rest of this region is also rotating. So this line rotates. So we get something on that side. And then this line rotates. We get it that side. And this bit, we also get a nice little circle. And we'll get another one out here. Okay, so we get this funky cylinder-looking shape, only there's this weird hole in the middle. There's like a sinkhole. Everything is falling down into it. And we'd like to know the volume of this region. So we're going to proceed, as we always do, by partitioning up the line segment between A and B. And when we do, okay, we partitioned it up. And somewhere in here, okay, we're going to build a rectangle. Because, well, that's what we do, right? We build rectangles. And instead of just finding the area of this rectangle, which isn't what we want anymore, we want a volume, I'm going to take this rectangle and I'm going to rotate it all the way around. Okay, let's move over here for a second, see what that's going to look like. So if I take a rectangle and I'm going to rotate it in a circle, so what's going to happen? Well, I'm going to get another copy of the rectangle on the other side. And then everything is going to rotate around. So I get that, and I'm going to get one here in the middle, like that. And then, of course, this guy rotates, and this guy rotates. Okay, and so what I end up with is this shell, right? It's like a cylinder with another cylinder inside of it. And if this is a really, really tiny distance, then there's not going to be a whole lot of space in between the big shell and the little shell. But that space, that's what it is we're looking for. We're looking for the volume I get by taking this region and rotating it around. And it's actually the inside of this shell, not the middle part, but the stuff in between the walls. Okay, so it turns out it's not that hard to work out the volume of this type of a shell. So the volume here ends up being, well, you'd basically take the surface area formula for a cylinder and multiply by thickness. Okay, so the surface area of a cylinder would be 2 pi times the radius, so this will have some radius, r, times the height, okay, so you get a height, times the thickness. Okay, that's essentially what we're getting. And the thickness, well, remember that's going to be this distance here. That's always going to be our dx, right, when we go past to the limit. Okay, so this is going to be the radius of the shell. That's going to be the height of the shell. Okay, so how are we going to actually use this? Well, remember, we didn't just set this up so we could find the volume of this one particular cylindrical shell. We wanted to find the volume of this entire region, but all we have to do is add up all the volumes of these shells. Okay, so our volume is going to be equal to, well, we're going to integrate because we want to get all these different cylindrical shells. We integrate from A to B. Okay, now each one of them is going to be 2 pi times r. Well, what's r? R is the radius. What's the radius? Well, it's how far it is from the axis of rotation. That's what we did here. We rotated around some axis. It's how far it is from the axis of rotation to the outside of the shell. Okay, well, let's draw a little line here. And if the x-coordinate is, well, we'll just call it x. If the x-coordinate is x, the distance from the axis of rotation, which here is just x equals 0, to the middle of this rectangle, well, that's just 0 to x. That's actually just x. So that's our radius. Okay, so this x is our radius. Then we need the height. So the height of this rectangle. Well, the height in this case is just how far it is from the x-axis to the function. Well, that's just f of x. So that's our height. Well, and then we have dx. Okay, that's what happened when we passed to the limit. All right, so we get a slightly different formula than before. We still have, of course, the function involved. That's no surprise. But now there's an extra x factor out here, and instead of a pi, we have a 2 pi. Oh yeah, right. We're not squaring the f of x anymore either. Okay, so actually, substantial difference. Okay, so there's going to be a very drastic change based on whether or not you're rotating a function of x around the x-axis versus when you rotate it around the y-axis, at least in terms of the formula that we can cook up. Okay, let me erase this and we'll do an example. All right, welcome back. So in the previous video, we looked at this situation where we had the function f of x equals 2x, g of x equaled x squared. We had some area bounded in between them, between 0 and 2, and we rotated around the x-axis or maybe another axis. This time we want to go around the y-axis. So let's work it out. So the volume, we know we're going to get an integral. It'll go from 0 to 2. Those are where the functions are intersecting and what's giving us this area. And then this is, of course, not erased because this is what we need to remember. All right? It's not that formula from what we did before, but really this right here. The volume of one of these shells that we're going to cook up is 2 pi times the radius of a shell times the height of a shell times dx. Okay, well the 2 pi I can copy, no problem there. Now's when I need the radius of the shell. So here's a little trick. When you're using this cylindrical shell method, and you have two functions which bound a region, pick some point, we call that x, and draw a vertical line over x that goes between the two functions. Okay? Why do I want that vertical line there? Well, number one, I'm going to need the height, right? And that's actually going to be the height of a shell. So I'm going to have to know that distance. Two, I need a radius. And the radius is going to be exactly how far away x is from the axis of rotation. So this line is a very helpful guide. So I remember what I need to do with each one of these. So for the radius, well, I need to know how far away this point x is from the axis of rotation. But this is just 0. So it's from 0 to x. That's going to be x. Okay, again, that's my radius. Okay, next I need the height. So I need to know the height of the rectangle I'm going to get. And, well, that's pretty easy too here. The f of x is on top, the g of x is on the bottom, so I just need to subtract 2x minus x squared. And that will give me the height of my shell. And then, of course, I have my dx. Okay? That's all there is to it. Of course, you're going to work this out. I won't waste your time with that. What if, though, we didn't want to rotate around the y-axis, but around something else? Like, I don't know, let's say we wanted to rotate around, how about x equals 4? Yeah, so now we're going to rotate around a different axis. How is that going to change things? Well, we're still using a shell method because we're rotating around something which is parallel to the y-axis. But some of these things may have changed. Well, let's see. We're still integrating from 0 to 2. That's where the curves are defined. The radius, that's how far our line is from the axis of rotation. And that's clearly changed, right? That's clearly changed. Before we were going from 0 to x, but now we're going from x to 4. That's not the same thing. So how far is it from x to 4? Well, it's just 4 minus x, all right? If this was a 1, it would be from 1 to 4. You'd say, oh, it's 4 minus 1, 3. So 4 minus x. So I actually need to step in here and replace my x with 4 minus x. Okay, how about the height? Well, this line didn't change in any way, so the height is actually going to stay the same. Okay, this is a subtle point. You're rotating around a different axis. You need to go back in, change your radius, and compare, right? And the way it's always going to work out, whichever one is further to the right, that's what you're going to write first. Okay, so here, when we rotated around the y-axis, x was to the right. So it was x minus 0, but we just wrote x. Here, the 4 is to the right. So it's going to be 4 minus x. And that's going to be our radius. Okay. That's all there is to it, right? No problem. We'll see you next time.